This is a continuation of example number 1 for hydraulic jump in our trapezoidal channel. So here we have to calculate the power lost of the jump. So if this is the cross section of the jump and the depth before the jump is 1.2 meters and the depth after the jump is 1.8 meters. The hydraulic jump occurs in a trapezoidal channel. So if we have to get the section, this is the section before the jump and after the jump, and this is the depth after the jump is 1.8 meters. So they have the same side slope. The slope before the jump and after the jump, that is 1:2. That is 1 horizontal and 2 vertical. Okay, so we need to determine the power lost. So we have to find the power lost of the jump, and that is equal to gamma q times the head loss of the jump. Okay, the area of flow of a non-rectangular section containing hydraulic jump, we need to determine the centroid of the section from the water surface. Since in this problem, our section is trapezoidal section, and it is easier to determine the centroid of this section from the water surface by dividing this into triangle and rectangle. The centroid of the rectangle is 1/2 of its depth from the water surface. For this triangle, the location of the centroid is 1/3 of its depth from the water surface. Also, for this triangle, it is 1/3 of its depth from the water surface. The side slope of this trapezoidal section is 1:2, and also this one, that is 1:2. That is 1 horizontal and 2 vertical. This is our x. I will let this also as my x since they have the same side slope. And since this is for this section 1, that is the area of flow before the jump, this will be my area 1, but I divided it into rectangular and triangular in shape. So I will treat this as my area 1:1. This will be my area 1:2, and this is my area 1:3. The total area of flow, that is the area 1, is equal to the sum of area 1:1, that is the area of rectangle, plus the area of triangle, that is area 1:2, plus the area of another triangle, that is area 1:3. Since they have the same side slope, so area 1:2 is equal to area 1:3. Thus, the area 1 is equal to area 1:1 plus 2 area 1:2. So, solving x, we have by ratio and proportion when x is equal to, or x over y is equal to 1/2. So x, we will express our x in terms of y. So we have 1/2 y. Okay, so if we have y as y1, so your x is equal to, so x, we will let this one as our x1. Okay, x1. So our x1 is also equal to 1/2 y1. Okay, so for the area 1, for the area 1, 1, that is the area of rectangle that is equal to, okay, the base of the trapezoidal section is equal to 4 meters. So you have 4 times y. Our y is equal to 1.2. Okay, this is 1.2 meters. That is for section 1. For section 1. Okay, so we have 4 times 1.2 plus 2, 1/2 area of triangle, 1/2 base times height. So for x1, since our y1 is 1.2, so we have here x1 is 0.6 meters. So that is 1/2 0.6 times 1.2. Okay, we will solve 4 times 1.2. Okay, 2/2, this can be cancelled out, plus 0.6 times 1.2. Okay, that is equal to 5.52 meters squared. So we have 5.52 meter squared. Okay, for our section 2, okay, we will do the same for section 2. Okay, say the same section, that is trapezoidal section. We have to divide the section into rectangular and triangular section. So this is 1.8 meters in depth. So we have here, okay, this will be our section 2. This is our section 2, but I have to make this as my section 1 for section 2, and this is section 2, and that is section 2 of section 2, that is area 2, and this is the area of section 2, and that is the area 3 of section 2. So I have to write that one as 2, 3. Okay, the same side slope, we have 1:2. Okay, 1:2. Then for our x, this will be our x2, and this is also our x2. Then the bottom width is also equal to 4 meters. So for area 2, that is the sum of the area 2, 1 plus area 2, 2 plus area 2, 3. So since area 2, 2 is equal to area 2, 3, because in this problem we have the same side slope. Now we have the same side slopes. So if we have different side slope, we have to add the area, each of the triangle. So 8 to here is equal to 8 to 1 plus 2, 8 to 2. Okay, so again we will compute the x2. Okay, that is also equal to 1/2. So x2 is equal to 1/2 of y2. And y2 is 1.8. So x2 is equal to 0.9 meters. We will compute the area of flow of section 2. So area 2, 1, that is the area of triangle. That is 4 times 1.8. So 4 times 1.8 plus 2 triangles. Okay, that is x2, 1/2 x2. Okay, 1/2 x2. Okay, x2 is equal to 0.9 and the depth is 1.8. So we can cancel 2. That is 2 over 2. So we will compute 4 times 1.8 plus 0.9 times 1.8. So the answer for the area of flow for section 2 is equal to 8.82 meters square. Okay, that is for area of the section 2. Then we will also compute the area and its location of the centroids from the water surface. So we have area y1, yc1. Okay, for section 1, this will be our yc1. Okay, this is yc1 and this one is our yc12, c12, and this is also our yc13 for area 1. Okay, so area 1, the area 1 is 5.52. So okay, so we can write this one. Area yc1 is also the sum of area 1, yc11 plus 2 area. Okay, we have to simplify again. So okay, this is area yc11. Okay, area 12. Okay, area 12 yc12 plus area 13 yc13. So since this one are equal, so we can write yc1 is equal to y1 yc11 plus 2 area 12 yc12. Then we will substitute the values. So here for our area 1 yc1. So for the area 1, we have the area 1, this is 4 times 1.2. So we have 4 times 1.2 and the centroids for that is 1/2 of y2. No, sorry, 1/2 of y1. Okay, y1 here. Okay, this is your y1, that is 1.2 meters. Okay, 1.2 meters. So 1/2 of 1.2, that is 0.6. Okay, that is the location of the centroid of the rectangle. So we have 0.6. Okay, then plus 2. Okay, 1/2. That is area 12. Area 12, that is the area of triangle at section 1. So that is 1/2 0.6 because your x1 is 0.6 times 1.2. Okay, you have 1/2 times 0.6 times 1.2 times 1/3 of y1, which is 1.2, 1/3 of 1.2. Okay, that is 0.4. Okay, that is 0.4. So we will compute. This is equal to, okay, 4 times 1.2. Okay, again, 4 times 1.2 times 0.6. Okay, that is 2.88. Plus, we can cancel 2 over 2. So you have 0.6 times 1.2 times 0.4. Okay, you have 0.288. So, okay, 2.88 plus 0.288. So, the area, okay, your area 1, YC1 is equal to 3.168. Okay, this is in meter cube. Okay, next is for the area 2, that is area 2 YC2. So, the same for section 2, the location of the centroid of this is your Y2. Okay, that is YC2 1. This one is the location of your centroid. Okay, this is YC2 2. And also here, this is YC2 3. Okay. Okay, we have to add A2YC2. That is just the sum of area 21 YC21 plus area 22 YC22. Okay, plus area 23 YC23. Since they have the same side slope, so the area is equal to area 22 YC22 plus area 23 YC23 are equal. So we can write our formula for A2 YC2 is equal to 2 area 21 YC21 plus 2, okay, area 22 YC22. Okay, so we have to compute the area for section 2, that is the area of rectangle, sorry, that is the area of rectangle, that is 4 times 1.8. Okay, that is 4 times 1.8, and the location of the centroid from the water surface is 1.8 divided by 2, and that is 0.9. Okay, plus 2. Then for the area 2, that is the area of triangle, so you have 1/2. Your x2 is 0.9. Okay, and depth of flow is 1.5. So you have 1/2. X is 0.9. Depth of flow is 1.8. And the location of the centroid from the water surface is equal to 1/3 of the depth. So that is 1.8 divided by 3, and that is 0.6. Okay, 0.6. So we have to compute this 2 over 2. This can be cancelled. So you have 4 times 1.8 times 0.9. So you have 6.48. 6.48 plus 0.9 times 1.8 times 0.6. So you have 0.972. So 6.48 plus 0.972. So the answer is 7.452 meter cube. So that is area 2 YC2. Okay, for the velocity of the hydraulic jump in a non-rectangular section, we can compute the velocity before the jump. That is equal to V1 squared is equal to GA2 over A1 times A1 YC1 minus A2 YC2 all over divided by A1 minus A2. So, we will substitute all the values in our formula, and this will be equal to G is the gravitational acceleration, and that is 9.81. The area 2, okay, the area 2 is equal to 8.82. Okay, that is 8.82. Area 1 is equal to area 1, 5.52. 5.52. And area 1 YC1, that is 3.168. 3.168 minus area 2 YC2, that is 7.452 all over divided by, okay, A1 is equal to 5.52. Area 2 is 8.82. Okay, so this will be equal to, okay, 9.81 times 8.82 divided by 5.52, okay, times 3.168 minus 7.452, okay, divided by 5.52 minus 8.82, and that is equal to, okay, 20. This is V1 squared, that is 20.349. Okay, therefore V1, we will take the square root of that. Okay, that is 4.511 meter per second. So we have our velocity for before hydraulic jump will occur. And since flow rate is constant all throughout of your channel, so we can determine the flow rate by, okay, the flow rate in the canal, which is equal to area 1 V1. So the area of section 1, or the area before the jump, that is the area of the flow rate before the jump, is equal to 5.52, and the velocity before the jump is 4.511. So therefore Q is equal to 5.52 times 4.511. So that is 24.901. Okay, 24.901 cubic meter per second. After computing the rate of the canal, we can now determine the velocity after the jump, and that is equal to V2, which is equal to Q over area 2. Since Q is constant all throughout of the channel, our Q is equal to 24.901 divided by area 2, that is equal to the depth after the jump, or that is the area after the jump. So this is equal to 8.82. Okay, that is 8.82. So 24.901 divided by 8.82, that is equal to 2.823 meter per second. Okay, that is the velocity before, that is the velocity after the jump. Next is to determine the head loss, because we need to determine the power loss in the jump. So for the head loss, you have the difference between the specific energy before and after the jump, where the specific energy before the jump is equal to y1 plus v1 squared over 2g. So this is equal to y1, that is 1.2, plus v1 squared, that is 4.511, divided by 2g. So this is equal to 1.2 plus 4.511 squared divided by 2g, that is 2.237 meters. The specific energy after the jump is equal to y2 plus v2 squared over 2g. The depth after the jump is 1.8, and the velocity, that is 2.823 squared divided by 2g. So 1.8 plus 2.823 squared divided by 2g, that is 2.206 meters. Then we have to compute the head loss. We have 2.237 minus 2.206, and that is equal to 0.031 meter. Therefore, the power lost is equal to gamma, the specific weight of water, times the discharge or the flow rate, times the head loss of the jump. So that is equal to 9.81 times 24.901 times 0.031. So the power loss of the jump is equal to 9.81 times 24.901 times 0.031, that is equal to 7.572 kilowatts. Okay, so this is the power loss of the jump. This is our final answer, so we need to encircle our final answer or box our final answer. So again, the power loss of the jump is 7.572. I hope you understand this problem, and thank you for watching this video. God bless.